little specific because it's not going to be like about a new element of the course like they usually are. So this one we're going to go over stuff that you've usually already seen, and we're going to add like a little supplement which should help you with the homeworks and with deep learning in general. So that's about debugging and visualization. So yeah, so that's what you know. You know what neural networks are, and you know how to train them in theory. You know how to use PyTorch to do that and to do a bunch of stuff. And you have homework 1, part 2 on which to work, and you should have started, I hope. And if you have started, you may have noticed that it's usually not as simple as you may think it is from like the code that we give you in the recitations, because you think it should work, but usually it doesn't. So that's true in computer science in general, but I think in deep learning it's even more accurate and more frequent and more basically the debugging part is going to be more important. So yeah, so usually you have your model, you have your training. It doesn't like raise a syntax error. You think everything's fine, and nothing works, and you don't know why. So that's what we're gonna go over today. So there's gonna be like a bunch. It's more like a good practices recitation, if you want. So you're invited to try all the things we're gonna talk about as soon as something doesn't work. Like go over the slides and find what kind of problem you have, and do that. And if nothing works after that, go to office hours. So that's the kind of errors that you could get. It can be based on Python. It can be based on PyTorch that you didn't use correctly. Or it can be just that you have a plus or minus that you inverted, and so all your math is goes berserk. Or your model can be bad, or your optimization parameters can be bad. Or all of these things are good, but the accuracy still doesn't increase for some reason. So we're not going to go about Python errors in the specifics, because well, that's beyond the scope of the course. The PyTorch classical errors, you've seen them in Recitation 2, so I'm not going to repeat them. But what we're going to do about these components is like see ways to organize your code and ways to find where the errors might happen. So there's going to be like a part about like code organization, followed by a part about model-related errors. So like that's everything related to like model training and testing. And then there's going to be a part about visualization, which is a tool that's going to help you do all those things much more easily. Any question until now? I guess not. So yeah. So first coding tip. This one is, yeah, I should mention it's probably going to be a short recitation, so you'll have time for questions kind of whenever you want, including at the end. So your code should be modular. That means it should be divided into small components. The components do a task, and you know where to find them, and you know how they call each other, these modules. And that's like a general thing that you do in computer science. Here it's all the more important. One of the applications of that is that you should avoid notebooks. So that's an important one, because a lot of people from last semester did their homeworks, the part 2 and stuff, on notebooks. I highly recommend that you don't do that for like most of the code. Notebooks are great like in a course, because you can put like comments and tutorials in the middle. They're great to do scripting and try a bunch of stuff, because you can like run a part of the code and run it again, etc., because it's like interactive Python. But if you have like a system and you want to know what it's doing from the beginning to the end and how to change the parameters and stuff, it's terrible. So don't do your homeworks on a notebook. We'll do the recitations on a notebook. It's possible that one of the homework part 1 we give you on a notebook. Don't do the Kaggle things on notebooks. Except like you can have like once all your models are coded, you can have like a script file that you just call once, and it runs like everything in a proper order. So that can be a notebook. Yeah, centralize your hyperparameters and like code parameters in general. So like everything you could change that is not like a model parameter, strictly speaking. So the thing people usually do is like like when you want to define the learning rate, you just put like when you define your optimizer, you model learning rate equals 0.001. And you do the same kind of things for all of your hyperparameters everywhere in the code. Don't do that. Instead, what you should do is have like centralize all the things that you can call like configuration parameters. You can put that in a file, or you can send all of them in the command line of your script if you prefer. But basically, centralize them. We're going to see an example very shortly. Yeah, final, I think, general coding tip is to start small. So when you have like a task that you want to do, you start with the simplest model possible. You don't allow it to be to have like a lot of configuration for now. And once this works, you can add stuff incrementally to make it more complex. So like a kind of like an application of that is that you should have a sanity check in your code. You know what that is in general? No? Okay. Sanity check basically means you do everything your code is supposed to do, but like in a toy environment. Like for example, if you were doing deep learning, instead of applying the sanity check would be instead of applying the model to all of your data, you'd apply it to like the first 10 elements of the data and only that, and see if everything goes right, so to speak, in that context. Not regarding like the validation error loss. It's going to be much worse than if you are training on the whole data. But more generally, will your model look fine if you do this kind of thing? So sanity check is like a general term that means do everything, but in the smallest environment possible that allows you to check that everything seems right. So yeah, you can check an example. So it's on the GitHub for Recitation 4. You should have access to that. So that's basically the way I do all my models. You can do that, or you can do something else, but like it's based on my own experience. You can copy this. It's applied. This one is applied to like MNIST, so it's like super simple. You can take it like as a skeleton for your homeworks if you want or not. All right. So the script file is this one. So it has just one method. It almost doesn't do anything. It just calls the loader. It creates the model. It can like have a parameter to load it from like a file. Yeah, another like small tip, it's good to save your models and to load them. Eventually have an option to load them, because like if you interrupt your training on AWS for some reason, it's a good idea to start over from where you stopped. Got a train function, and that's pretty much it. There's a function to like predict an input, and so you see it's super small. So the whole point of this organization is that when something goes wrong, it's going to be much easier to know where it's from. So I like to have a path file too, where you store like all the the relative paths of all the files you're going to use. So that includes the data and that includes where you save your model. So that way you can't be wrong. And you've got one file for the data, one file for the model, and one file for the training apart from that. So routine is the file that holds all the training and validation functions, everything that can run, basically. Let's start with, data defines the data loader. Model, so what I have is I have a class, and I don't pass it like the parameters or the number of layers in arguments. Yeah. I guess I can make it larger, yeah. Better? Okay, sorry. Yeah. So I created a class inherited from sequential. So this code should be like very familiar with you right now, I guess. I just like I initialize my model in a little like trick way that allows me like to configure it, but not to add a forward method because it's already like a sequential class. But that's pretty much it. So there's nothing surprising in the code. It's just that the most important thing, I guess, is that I don't pass arguments for like the layers and the parameters. I just go into the configuration file and I read what's in it. So like, I'll just open the configuration file right now. So yeah, it's just a list of attributes. So I have like a flag for CUDA. I have a flag for like the sanity check. So like for example, for the sanity check, if I go back in data, you see that if the sanity check is true, I just look at the first 150 line of the data file. And there's a few other things that change, but it's this kind of examples. You have information about the data. So this one is like based on the data set. It's not going to change. These are all parameters that I can change whenever. So that includes the number of dropout, the number of hidden layers, and the size of each hidden layer, etc. So the configuration file is called in every of the other files when I need to access one of the parameters. So yeah, I overwrote the sequential for the model by adding a load and a save function that go in the path and like look at where the model is. I'm not going into much detail because it's all stuff that in the detail you have seen it. It's just like what's important is the organization. And then there is the train function to which I pass the data loaders. I have a run one epoch function that does most of the work. There is a stop when the validation loss stop increasing. You can look at that. So it's kind of like, it's basically early stopping implemented. So you can look at the details of the code. I'm not going too much into that. And there's a prediction function to apply to the test. So if you want to go to like overwrite all of this to make it work for homework 1 part 2, that's allowed. If not, just like keep in mind the general ideas of these parts of the recitation. Like, I'm just gonna from Carnegie. Yeah. So modularity, configuration file, and small to large in your model. Right, now we can go in the, so that was like the prevention parts of the recitation if you want. I don't have access to the time, I'm just gonna check. I wanna be late. Yeah. So, in the debugging, so basically if I reorganize a little bit the things we've seen in the first slides, the three kinds of error you can have is a code-based error, a training-based error, and a testing-based error. Coding error would refer to when you want your model to do something specifically for following like a computation graph, and it doesn't for some reason. Training error is when it does follow your computation graph, but the model still isn't learning as well as you want it to be. And testing is when it is learning how you want it to be, but when you try to print the final result, they are still terrible for some reason. So the last one, in a like classification example, it's rare that it happens. We're going to have a slide about that, but it's only going to be important when you deal with like sequential input and output in homework 3 and 4. So we're not going too much on that part. So generally speaking, you should first wonder, do I have a coding error? And if you've removed that possibility, look at training errors. So coding errors, basically the signs would be that your loss doesn't decrease at all. If it decreases a little bit, it's probably like a training error. But if it's doing nothing or it's going the wrong way, it's probably a coding error. or that the outputs don't change, or that the training stops because you've taken too much memory at half training and it shouldn't happen because your batch is small and everything. So if one of these things happen to you, and or more generally, if you think you have a coding error, well, basically the solution is to print a bunch of stuff to look at the first moment that something seems to be wrong. So the thing you should print, there is print your data, like print the first element of like a batch, look if the instance and the label seem to be aligned compared to what the dataset was, because it's possible that one was shuffled and the other wasn't, or that you're not iterating on the data because you mishandled your getItem function in the dataset. You can look at the shapes of everything in the forward function of your network or your weights, see if everything seems consistent. You can try to print your hyperparameters, compare with the configuration file, see if they're okay. You can check your parameters. So if you, in a network, if you do mynet.parameters, that's a generator for all of the parameters of the network. So you can just print them that way and check that they're actually changing from one iteration, one batch to the next one after a backward. And you can go into wonder if, like, maybe when you try to do something complicated, the code fails. But maybe if you do something more simple, like using a batch size of 1, it might work. So trying all of these things should help you finding coding errors. So that's the kind of things where you're very happy to have a sanity check implemented. One of more less threatening but still painful kind of error is the time issues, like when things work but they definitely should be faster than how they are. So in that case, you have like the time module. You can check the length of like each of the steps of the subtask of your code, like the data loading, the backward, the forward, and see where it seems to fail. So that's the kind of like reflexes you should have when you're coding deep learning. That's pretty much it for the coding errors. I don't know if you had questions about that part. If not, I'm going to go into the training-related errors, including the model. Yeah?
Could you talk about like parallelization while doing data prep and all that, especially when we have large data sets? How do we deal with that?
How do we what, sorry?
How do we deal with like large data sets when we have to do data prep?
So you want to like...
So like, is there some sort of parallelization that you suggest using, or can we like split the data into parts and process them and then use them? Or
what? You mean if you don't have enough memory in the code to run that? Yeah, that might happen. I'm wondering if that might happen in homework too. I think it shouldn't. How you would do that if you don't have a large enough PyTorch, GPU memory on your machine. There are some methods in NumPy where you can sort of like have an array in memory, but in reality, it's having just what it can have of the data in the memory, and the rest is is still like in the hard disk. So you can look at that. I don't remember exactly what the function is called, but there are stuff to do like that, and they have bindings with PyTorch. So there are things designed to handle specifically this case. I just don't have the functions in mind. But I don't think it should matter too much for the homework that we're going to give you. Definitely not for homework 1. Training errors. So, yeah, so that's basically one big sign of that kind of thing is your loss would decrease, but just not enough. So how to know how not enough is, so you look at your loss. If the loss is random or worse, it's probably a coding error. If it's better than random, it means that you are actually training one way or another, but not well enough. So that's the training error case. So a classification model, if you're wondering what random is in reality, you can look at the definition of like cross entropy. And you'll see that basically a random classification model, the loss would be about the logarithm of the number of classes. So if it's better than that, you know that you're doing something. But check that the initialization isn't enough to get better than random, because that's also possible. So if you're in the training error case, I'm assuming you've removed the possibility of a coding error case. So then even there you have like different kinds of problems. So it can be your model that's not good enough to learn the patterns of the data. Classification context, it probably just means the model is too small, because there aren't that many things that you can do badly. Or it can be that your model is fine, but you're just not training it correctly. Or it can be that you're training your model too well and you're overfitting on the training data. So we're going to go over this kind of things. First, if you want to make sure that your loss is not going down well enough, you should remember that models, if you train them too long, they will overfit. So usually that's something you don't want, but it's also something you can use for debugging purposes, because if you train your model on a part of the data, and you look at the training loss, just the training loss, it should go to 0. So that's not something you want in the training, but if it doesn't do that in this specific context, that means you have a problem. So that may help you find it. Now, if you're wondering if your model is too weak, it's good to have like orders of magnitude in mind. Unfortunately, there aren't that many deterministic rules to find the good size of the data. From experience, we give you you already find on Piazza examples of sizes of models that should work in homework 1 part 2. Basically, if you don't get accuracy of half with like 3 layers with small sizes, you definitely have a training problem, because but not that model is too weak, because that's good enough. So if you don't think your model is too weak, that's where you should look for optimization related issues. So all these things, they kind of overlap with Recitation 3 and with the course, so I'm going to go fast on that. So if your learning rate is too small, you may learn too slowly. If your learning rate is too large, you may learn fast at the beginning, but suddenly you stop learning. So these are all the kind of things you should play with to check if you're doing something wrong. So there is the learning rate, the kind of optimizer you have, the kind of initialization you have, the size of your batch, or the kind of batches you have in like more complex context. But for now, let's just say the size of your batch. So I did print-ins of stuff that are like default goods. That means like the things that usually people do in general, but that doesn't mean they're gonna be okay all the time. But if you have no idea what kind of learning rate or what kind of optimizer to use, take Adam and use learning rates 0.001. In general, that's a good place to start. You should still try to change stuff, but it's a good place to start.
Question?
Yeah.
May I have some questions about the batch size?
Yeah.
Because I think when we have maybe 100,000 instances, or we have 10 million instances, does this mean that we would have the same batch size, or if we have more than 10,000?
Good question. I think it could make sense to have to take larger batch size if you have more data, because then you have more iterations to look at. So yeah, these are things to like take into account. But then again, I don't have like a specific math rule that's going to give you, given the size of this data set, this is the correct batch size, because that doesn't exist. But yeah, you can take, if you take a batch size of 128 and you're wondering why things don't work, and you wonder, okay, with this batch size, I only have 500 iterations per epoch. That's maybe not enough. I should decrease the batch size. Yeah, that's a good reasoning to have. Then again, I don't have like an explicit rule.
And by the way, so if we use different optimizers, do
yeah.
we need to choose different batch sizes for different optimizers? Or, I mean, would the batch size have a big impact on the performance of my optimizer?
I don't have a rule on that. I think the batch size I give here are like, I've seen them happen in papers with all different kinds of optimizers. So I don't think there is something like well known and established that gives this result, although it's possible that it does hold some truth somewhere. However, kind of related to that, you usually, if you use SGD instead of Adam, you're going to need a bigger learning rate. That's true. 0.001 is something that works well with Adam and adaptative methods in general. If you're doing something not adaptative, you might want to remove a 0. Yeah. So if you don't have an optimization issue of this kind, it's also possible that your model is actually not too weak, but too complex, and therefore it's you have like a vanishing gradient problem. So then you should try to remove layers. Yeah.
So I thought that if we have the same numbers of neurons with the same number of neurons with deeper network, it could prevent overfitting. Why?
Well, even if you
So what was the question again?
So I saw this week's lecture. It says with the same number of neurons, but with a deeper network.
So the deeper network can do a better job of representing your function, but learning the network ends up being much harder.
yeah. Because I was more in like the vanishing gradient problem than the overfitting problem. But even there, if you augment the number of layers, not changing the size, but do 10 layers instead of 5, you have more chances to overfit on your data. But maybe what you're saying is that you have less chances than having like 5 layers, but you do them 10 times bigger. But in both cases, when your model is too large, whether the dimension, you have a risk of overfitting. And if the model is too deep, you have a risk of vanishing gradients. But we're going to go into overfitting actually right now. So the symptom of overfitting is like actually simple to diagnose, because it's when the training loss decreases, but the validation loss doesn't. It's as simple as that. Just to identify one of the reasons you want a validation set all of the time is that you want to diagnose overfitting. So do it. If you don't have a validation size in the data set, you create your own. It's like essential. So if you do have an overfitting problem based on validation loss and training loss, well, in order, the things you should do, I guess, are verify that you shuffle the training data correctly, because if you don't, you're in the problem seen in the lecture. Actually, it's not exactly the problem seen in the lecture, but nonetheless, if you don't shuffle your training data, you overfit more on the training data, because you very like intuitively you don't have as much generalization from the model's perspective. It's always the data in the same order that shows up. You should verify that your model size and depth are make sense with respect to what literature draws or what your friends have for the same task. And you should definitely look at all of the things that you have seen in the lecture that I'm not going back over, that are dropout and batch norm and early stopping, rate decay, and all of these things that are all of them ways to prevent overfitting. Like dropout, it's actually all it does. It's you change your data so that you generalize better. And it's important to know, I guess, that adaptative optimizers like Adam tend to overfit more than non-adaptative like SGD. That doesn't mean you shouldn't use them, but you should still be aware of that. So that was for overfitting the simple case. interestingly, you can also overfit on the validation set, key, which is usually used to detect overfitting. But if you tune your model a lot and you use always the same validation set, what's going to happen is that you're going to find, by changing the hyperparameters, you're going to find by accident a model that works well on validation but won't generalize to the rest of the data. So that's much harder to do, but if you tune long enough, it might happen. So an application of that is that if you do homework 1, part 2, and you do a stupidly large amount of submissions on Kaggle, you're going to tune your model on the public leaderboard, but you're going to overfit on it. And so when we look at the private leaderboard at the end of the competition, you're going to be very disappointed by what you get. So keep your submissions modest. And if you want to look at many architectures in general, don't use like one validation set, but look at things from machine learning that might be better, like k-fold validation, when you try like different models with different validation sets. And I'm not going to go into detail of what it means, but if you Google it, it's going to show up. Finally, about the testing issues, just like one quick slide on that. So sometimes it's possible that your model actually learns, the training loss decreases, the validation loss decreases too, you don't overfit too much, and then you try to print your outputs and suddenly it doesn't work anymore. So that might happen for two reasons. First, because you messed up the function that's going to output the results, or because if you recall, the losses that you use, you don't use them because that's what you want to optimize, but you use them because it's a differentiable approximation of what you want to optimize. But the approximation is not perfect, so it's possible in the general case that your loss is very good, but your accuracy is very bad. Although in simple classification tasks, I wouldn't see that happen too often. Again, we are gonna go back on this when we're doing sequences in like later parts of the course with RNNs and stuff. Now I have okay. We're basically done with the first part of the recitation. Just one thing, I told you should look at your loss and your accuracy and everything. But if you just print them in the terminal, it's gonna be pretty bad to look at and hard to read, and that's one of the reasons why we have visualization, which is what we're going to talk about now with TensorBoard. So I'm just going to pass the mic to Sarvesh. Maybe before, did you have any questions about this part of the recitation before we move to something else? Yeah. The loss always goes zero. If the loss goes zero, that means you're training perfectly, which means you're probably overfitting. So again, that might be a feature if you're verifying that your model works. You can look if the loss goes to 0, 0, 0. But in general, you're gonna want to stop before the training loss reaches 0, unless your model is so good that it can get the full points even on the validation set. But like for homework 1, part 2, for example, you should not expect your loss to go to actually 0. That would be 100% accuracy. It's impossible. Yeah?
You mentioned that we can accidentally overfit like the 30% of the data used on Kaggle for the public leaderboards.
Yeah.
So when it comes to the private leaderboard, does Kaggle take of all your submissions the one that scores highest on that 70%, or does it take of all your submissions the one that scored highest on the 30% and then choose that to score on the private? Does that make sense?
It's gonna choose the one that fits the best on the public leaderboard, unless you tell it to choose another one. So if you think one of your submissions was good by accident, quote unquote, on the public leaderboard, you should pick another one and say, Kaggle, I want to use this one for the evaluation. You can in the submission, there is a case you can specify. Pick this CSV file for the evaluation, and then it's gonna look at the the results of this submission on both leaderboards. All right. Recitation, visualization.
Connector for Adobe. Do you have a TensorBoard setup on yours?
Ooh, good question. I don't know. Maybe we should use yours.
No, I don't have a I don't have a HDMI connector. Anyone has a HDMI connector? Mac
Basically,
to
I'm on Windows, so I don't have anything right now.
And if you have a Mac to HDMI adapter, by any chance?
At home. Sorry, I didn't bring it today.
Can you post on
So-
Slack? I don't need it immediately, but when I'm running the code, I'll need something to show.
Well, do that now, and I'm gonna install TensorBoard in the meantime.
Okay. I will need the presentation.
Sure. Yeah.
TensorBoard on your own laptop.
Yeah, but I don't have a HDMI port, and I have
There is
Is there a VGA connector?
there, I don't think there's a VGA connector, but there is a USB connector. Maybe that would work. I don't know.
Try it with USB.
I'll try running that. No signal detected. Will it work if we put something in the USB?
I mean, I don't know if that'll work. I mean, you can try it, but probably. Hold on. Is it auxiliary? I don't think that'll. Yeah, I don't know if that's. Flashes and then the signal's detected, but I think it is. What is this? You need a USB-C adapter, right? Because that's.
Is there a HDMI? Is it there's a VGA output?
Yeah.
There's a VGA. I have a VGA adapter.
Yeah, there's you either VGA or HDMI would work if you either one of those.
Oh, I have a VGA.
Oh, you do?
Yeah.
Okay.
Yeah.
Yeah, sure. I'll just unplug this. And, hold on, let's just do this. So it works. It's like a.
Yeah.
Perfect.
Sorry for that.
You have the mic?
Yeah. So basically, what we're going to look at right now is how to visualize your model on TensorBoard. For those of you using TensorFlow, I think the installation of TensorBoard comes along with your TensorFlow installation. And if you're installing it with Conda, I don't think you need to install TensorBoard explicitly, but if you've used the pip installation and you're using TensorFlow, then you'd want to install TensorBoard by using these commands. And for PyTorch users, TensorBoard X is what has been, recently, the package has been recently released for PyTorch users or other frameworks. You can easily install TensorBoard X, and it has pretty much everything that TensorBoard on TensorFlow does. So those of you who want to go through the code runs on the Jupyter notebook, you can download the notebook and have this installed, so you can run through it along with me. Now the need for visualization. So the basic thing about looking at your model is not just seeing how the loss decreases or increases, and that wouldn't actually just give you how well your model is performing on the given data set. You'd also want to actually visualize on a larger scale. Let's say you start off by plotting it on a graph, and you see, does it improve in the beginning? Is it very stagnant? The loss is very stagnant at the beginning, and then it makes improvements much later. Or how does the gradient change over time? Does the mean of the gradients move from 0 towards a different value? And also looking at the gradients, the way the gradients change over time will help you analyze or look at your model and say, do you want to add more layers or do you want to remove some layers? Like if the gradients, the plot of the gradients does not change over time. The mean is at the same position, and you're actually pretty much looking at the gradient in the same way throughout throughout the whole time you're training your model. Then you would want to like maybe reduce the number of layers on your model. And also for early stopping, like when you start seeing that the training loss is continuously increasing but validation loss has saturated or it has started going up, then you would want to like immediately stop. Other things that you can see or predict by visualizing your model is the weight initialization. When you initialize your weights to 0, you can see how the gradient, the plots of the gradient changes over different layers and how it changes over time. While initializing it with the Xavier or uniform initialization, and you can see how it changes over time on your model. And other things that you can easily choose for your model are the activation functions. Does it change? By looking at the gradients over time, you can also say which activation function performs better for the given data set. Is the dropout rate too high? And in general, it's a good way to optimize and fine-tune your network and choose the best hyperparameters that your model would work best on. Now, TensorBoard is basically a logger. It's a visual logger. Instead of logging all your losses, accuracies, weights into a file or onto your terminal, you would rather want to see it visually, and looking at it visually helps you determine a lot of other things. And here I have actually given the APIs specific to TensorFlow, but I'll also be discussing the APIs that correspond to PyTorch as well. Like in tf.summary is the publicly available API that's available for use in the TensorFlow domain. But for other frameworks, you'd be using TensorBoard X, and the API that's available for PyTorch or Caffe and other frameworks is the summary writer API from TensorBoard X. It allows you to log these values into user-defined directory. Like you can choose where to log your events into, and you can also log a lot of operands, images, audio, text, videos, and so on. So let's discuss a few things that you would want to use from TensorBoard or TensorBoard X for the homeworks in this class. The first thing would be the scalar logging. In case of TensorFlow, it's called, you log it using the tf.summary.scalar function, whereas for PyTorch or on TensorBoard X, you would want to use the summary writer.addScalar function. And what it basically does is it plots a 2D plot where the x-axis is your time axis or the number of epochs that you have run your model for, and the y-axis tells you what's the value of your particular operand that you have passed to the summary writer. And it's used to keep track of scalars like the loss, the prediction accuracy, your learning rate, if you're decaying the learning rate, your weight decay or the L2 decay parameter, and other unit one-dimensional scalars that you would have throughout your model, throughout your training. We'll actually go through all these things from the notebook once I go through these slides. And the second thing is the histogram. So basically your gradients or your weight matrices are two-dimensional matrices or tensors. And to look at a two-dimensional vector, you would want to see that in a three-dimensional format. That is, over time, how do these gradients or your weight matrices change? And the best way to look at these gradients or weights is to plot a histogram on these cells. So what you would do is on the z-axis would be your time or the number of epochs. Your x-axis is the value of the operand. So in your weight matrices, you will have different weights initialized. Let's say you put them into bins, maybe that fall the values that fall between minus 0.01 to plus 0.01, 0.01 to 0.03, and so on. And then you plot how many such values exist in that particular block. And then you have you should have one of these as for a given instance of time, you'll have one such bell curve, and when you go over a multiple number of epochs, and then you'll be able to see like how those gradients change. So if you see here, the bell curve at the very end is what we have initialized it with. You can see that the z-axis goes from 0 to 400, and this is the plotting of the moving mean from the model, and you can see that the mean of the weights actually moves from 0 over here to 5, and this shows that your model is actually performing well. It's diverging from the mean that from the weights that you've initialized in the very beginning. And the other thing that you can also choose to visualize is using the summary.images or summary-writer.add images. What it helps you to visualize is when you're looking at a CNN model, you would want to see the heat map of where your gradients lie, like what are the parts of the image that you're actually looking at when you go through each training data or your dev data, and see what part of the image does your model actually look at to predict a particular output. And it's not just for images, you can also plot confusion matrices. So if your values do tend to be from 0 to 10,000 or so, the summary.images function, it automatically normalizes it for you, so you don't have to like normalize it to pass it to this particular function. Other things you can visualize are the CNN kernels, filters, and also your input images over different layers. Like you want to see what are the things that your model is actually, how does your model look at the input image over different layers. Then you can actually plot your inputs into this summary images. So if you're training on AWS, generally TensorBoard or TensorBoard X should be, again, you should start a server to view your outputs, and you would be using the command TensorBoard X --log there, and pass the directory that you're logging all these events. And when you're doing it on AWS, you would want to tunnel your port that is being created on your AWS instance. You would want to so that you can see it locally. Like for your homeworks, you would be using the AWS instance and getting a particular link so that you can like log in to the Jupyter Notebook from your local computer. But for TensorBoard, you'll have to run the server on the instance, and that will be on a specific port on the instance. So you'll have to like forward that port onto your local system, and this particular command ssh-i. Your machine port should be the port number that you want on your local system. So if you want it on 8000 or 8889, because 8888 should be the port that you would be using your instance on. So you would want to use a port that's free at the given time. And yeah, we can go ahead and see. Right. So for the recitation purpose, we'll be looking at the problem that was discussed in Recitation 2. Basically, the problem that states given your circle coordinates, the x, y, and the radius, and you have a point, you have to your model should figure whether that point is inside the circle or is it outside the circle. So before we begin, so this writer is equal to tf.summary.filewriter.logs. So you're actually creating a writer object that we use throughout your program, and this is where you would be logging every single event or every single scalar or images or weights of yours. And I'll be discussing the basic flow in TensorFlow and TensorBoard. Towards the end, there's also the PyTorch version with TensorBoard X, and it's pretty much similar. I'll quickly go through that also. So the first code block is to import all your packages. So this you have to now to get the data that we'd be training on. I'm going to use the same function that was available in your Recitation 2 notebook. And we are actually getting 10,000 points and their corresponding labels to check if they are within the circle or not. We'd be using right. And then we'll be using 500 points for validation. And if you print their shapes, you can see that the X is it has two different feature vectors, that is your X1 and X2, and the on a two-dimensional space. And your Y train is a single-dimensional vector because you're just it's a binary value, 0 or 1. If it's lying outside the circle, then it's a 0, and then if it's lying within the circle, it's a 1. Now we are making the writer object. We're going to log it into logs, and within the logs directory, we are creating a train directory, and all the events that we'd be performing through this particular run would be logged in the train directory. So you don't have to like explicitly create this directory. If it does not exist, TensorFlow or TensorBoard creates it for you. So the build graph function is basically the TensorFlow version for making your model, creating your model. Here you have X, Y, and GS. So X and Y are the same X's and Y's that you created the points for, train or validation based on what you call it with. And the number of units in each layer would be 12. The number of layers we're using is 2. Since the problem is not a very large problem, 12 units should suffice. And then when we're creating the network, we have 2 layers. We're just looping through it. And we're creating a dense layer, which is pretty similar to the linear layer from PyTorch. We are initializing it with 12 units. We have layer 1, layer 2. We're naming the layers layer 1 and layer 2 so that it's easier for us to visualize it on TensorBoard. And the kernel initializer is initialized with the weight init that's passed to the function, and bias initializer based on whatever the bias initializer you pass to the function. The Glorot uniform initializer is pretty much similar to Xavier initialization in PyTorch. And then you define a logits layer. So this is the layer that will be outputted from the network, and this is what you use. Send to softmax or the cross entropy loss. In TensorFlow, you use the sparse softmax cross entropy loss with logits, and in PyTorch, I think it's just the cross entropy function. The criterion you would be using is the cross entropy one, and then we have an Adam optimizer, and now over here we're actually computing gradients, and then for each of the gradients we're going to visualize these gradients using the histogram, tf.summary.histogram, and then we give a name to the gradient and pass the weights, the gradient that was calculated for this particular run, and we can log scalars at the very end of the loop where the loss and the accuracy is logged into the summary, and also we log the weights, and at the very end we merge all these all the different scalars, histograms that we've created into one summary operand, and then we pass that out as we return that as one of the parameters at the very end. So now we look at multiple different runs with different weight initializers, so that we know, like, initializing it with 0, how does the model perform when you initialize the weights with 0, and how does the model perform when you initialize it with the weight initializer like Xavier or a uniform initialization. Over here, we're going to run the ops for TensorFlow, and we get the summary object from the build graph, and we use that to look at on TensorBoard. Now, you're building the graph with a random uniform initializer so this pretty much is a uniform initialization between minus 0.01 and 0.01, which is very close to 0. And we're going to run the model for 200 epochs. All right. So I'm actually starting the server. So when you're running around AWS, you would want to use the SSH command, and then just use your web browser to look at the your local host at the given port that you're tunneling it into. So here, so this is basically what we have. So we plotted two scalars, that is the accuracy and the loss. As you can see that the loss is pretty constant for the first 40 epochs, and then the loss actually starts decreasing and then it starts increasing over here. That's the accuracy. The loss actually starts decreasing much later at like around 80. It becomes stagnant from 40 to 120, and then it starts decreasing pretty well. And the accuracy is at 50% for the first 40 epochs, then it starts reducing, and then you start seeing a good hike in the accuracy. If you go to the histogram section, you should be able to see how your model your gradients and the weights have been performing. So this is bias. These are the weights, kernel 0. And then you can also see the gradients that have been plotted over here, the bias 0 gradient and the kernel 0 gradient. And then you can see them for different layers. So layer 1, these are the ones for layer 1, this is for layer 2, and this is for layer last. These are your logits layer, or the layer that's coming out of that's going into the softmax function, the cross entropy loss, and these are the weights. So basically, when you see that we initialize the weights with zeros or pretty close to 0, you can see that the actual average mean is actually not changing much, though you can see that some of them are diverging, but the mean of your weights, the bias in the weights is pretty much at 0. Over here, you can see that the kernel weights are actually 0, but a few parts of the weight matrix actually diverge from 0 to minus 0.35, but this is pretty, you see this very often when you initialize it with 0. That's because you're multiplying everything with 0 and you're adding a bias of 0. So you don't see much of an improvement in your model when you initialize your weights with 0. you would want to use a different initializer like Xavier for seeing a better performance at the initial steps of your training. And now let's see how the model performs when you use an initializer like Glorart. So here I'm initializing the bias with a random initializer, but I'm not using any kernel initializer. So it's actually using the default initializer, that is the Glorart or the Xavier one. And if I refresh this, let's go back to the scalars. So you can see how the model is performed when you use a weight initializer like Xavier. So the accuracy actually starts improving from the very beginning, and it also reaches a better accuracy very quickly, whereas the loss is continuously decreasing, while in the previous for the previous one you actually saw that the loss was decreasing towards the very end, and it didn't decrease much. It was around the same constant values. When you go to the histograms, now you can see that yeah, so you can see that the mean of the your kernel weights were at 3 at the very beginning, and then it moved towards 0.1. It was at minus 0.188, and then you see that the mean actually moved to 0.1 over here. And so looking at these weights and the bias, how they diverge over time, helps you figure out like whether the model that you're using is good for the data set that you have. So basically, when you see that the mean of your histogram is not changing, you'd want to reduce your layers, because it's you're actually losing a lot of important data towards the very end. So over here, from the very beginning, the weights were at 0, but then if let's say you actually increase the number of layers in your model, you would start seeing that the first few layers have a good divergence in the kernel weights, but then as you move towards the last few layers, your weights would start, the histogram of your weights would start converging to a very small value, and you would want to reduce that layer. You want to remove that layer off from your model. Now, we can also see how different activation functions perform. So sigmoid and tanh have the issue of saturation, because you're trying to squash your outputs from the output layer to a value between 0 and 1 for sigmoid, and to a value between -1 and 1 for tanh. So if you have like if you have your output values to be closer to 0 or to be very high on either ends, then your values would your output values out of sigmoid and tanh would lie closer towards the 0 and 1 or -1 and 1, and that would not be the best way to look at the problem. Whereas in ReLU, what we do is any value less than 0 is cut off to 0, and it's a threshold-based activation function, and any value above 0 is kept the same way. So your gradients are actually calculated. The gradients that you calculate would would help in improving the model much faster. And one issue with ReLU is that values that are less than 0, you're actually putting them all, you're cutting them off all to 0, and that again is an issue, because any value that goes less than 0, you're going to keep it at 0, and using that to update your weights is actually at 0 is not doing anything to your model. It's actually going to keep that is going to update your weights. It's not going to update your weights that much. So you want to use leaky ReLU for those type of issues. We can see how the model performs for the sigmoid, tanh, and ReLU. Over here, I have defined 3 different directories: train sigmoid, train tanh, and train ReLU. You can see those directories on your instance. So wherever you created logs, you now have train and train in it for the two different things that we already saw. So once I run this, you should be able to see 3 more directories, one for sigmoid, tanh, and leaky ReLU over here. And within these directories, you have the events file that was created by TensorBoard. Now on TensorBoard, when I refresh, yeah. So you can see how sigmoid and tanh performed. Sigmoid was pretty similar to what we used in with the 0 initializer for weights, but leaky ReLU performed very close to what was being done in your initial function with the GloRart initializer. And the histograms can also be seen. It's not refreshed. Right. So you can see here that the kernel for leaky ReLU is very similar to the kernel with the GloRart initializer, whereas the kernel for sigmoid is the mean of the weights for their kernel is is all at the same levels, whereas for the leaky ReLU it's actually diverging over the number of epochs, over the 200 epochs. And then there are multiple pages, so you can see how the kernels at each layer of your model have diverged or converged. And then as you move towards the next few layers, you see that the kernels have actually started converging to a closer value. And now coming to the PyTorch implementation of TensorBoard X. So basically you import the summary writer API from TensorBoard X. Here I'm creating a sequential MLP with one hidden layer and one output layer. And we're actually using the same XTrain and train data set and the validation data set from what we created at the very beginning. And over here, I'm using the summary writer to create the logs directory. So there's a train PyTorch and val PyTorch. We're not using val PyTorch here in the next function, but yeah, the train PyTorch directory will log all the training scalars and histograms. We create the model, and now this is basically the function that you generally write for running your model. So we have the criterion, the cross entropy loss, and I have an SGD optimizer. You can choose to use the Adam optimizer, and over here, once I get the prediction and the accuracy, I create I add both the accuracy and prediction to the train log, which is using the log that we created above, the train log, using the summary writer, and I use the add scalar function to add the scalar operands, whereas I use the add histogram function to add the weights and the gradients. It's a very simple way to use TensorBoard X on PyTorch, and now when you run the model, you should be able to see the train PyTorch and the val PyTorch folders in your log directory, and also and your accuracies and losses that you have plotted on your graphs. I think the model ran for a bit longer over here. It ran for 1,000 epochs, and you can also see the histograms. Right. So this is a bit different because we used a different model and a different optimizer, but it's pretty much useful for finding whether your gradients are improving or your weights are improving in the model. And yeah, that's pretty much it from me. Yeah, thank you. Any questions? Yeah.
Could you possibly add a layer or two and show us how it looks when the layer is possibly not useful?
Right, okay. Just give me a moment. you can see here, I've used the GlowDot initializer for weight initialization. I've used 5 layers, and I've run it for 200 epochs and with 12 units. So if you can see here, the kernel graphs, the histograms for the kernel and the bias over multiple layers is very similar to what we saw with the zero initialization, right? It's not diverging much. It's all squashed in the same region. It's pretty, and if you see when you go towards the later regions, you see that the mean is actually lying at the center, and then there are few things that diverge towards the sides, but it's not much. So it shows that your model is actually performing poorly with so many layers. You would want to reduce the number of layers at this point, right? Yeah, any other questions? Thank you.
Just a general note to all of you. The TensorBoard stuff tends to be really important because you're going to run into problems with your networks all the time. This is just basically a fact of life that you live in. And you have two choices. You can come in Piazza and harass the PAs to fix your bugs and hope they will do it for you.